simple model can be dangerous. There are some more models. I will not go into the details of all of these. But it's just to mention. Here we say often not the failure rate is given, but the inverse, the mean time to failure. Okay, so when we have semiconductor metallization, this metallization fails after some time. It fails in a similar way as the filament of a traditional light bulb fails. So you have a light bulb that lives for a certain time, and then suddenly the filament is broken, and so no more light. So it's a relatively similar process in semiconductor metallizations. What is also important, it is much more affected by DC than by AC. So DC is worse because DC transports material in the direction of the electrons. So it's some ballistic. So if I take a piece of chalk and always throw it against your bottle could move. Yeah. Okay. In that way, it's a similar process, and the description is, of course, it is affected by the temperature in an Arrhenius fashion. But if you are able to independently vary the current density, then you could say the mean time to failure is proportional to the current density to the power of -2. That means if you double the current density, the lifetime is divided by 4. Yeah, that's a strong influence. That's a famous Black's equation for electromigration. That is a typical example of current or current density effects. On the other hand, also voltage has an influence directly. You have a dielectric material, so you can also call it an insulator. Yeah, it's a foil, or it's a gate oxide, or we have many dielectrics. Yeah. So when the dielectric is under voltage, so capacitor covering the dielectric, we have a certain field strength in between. And the higher the field strength is, the lower is the lifetime of that dielectric. We call that failure mode time to dielectric breakdown model. And so here we can say, yeah, in that model here, we even give the voltage, but the better property is not the voltage, but the field strength. Yeah? Because the field strength is the material property, the voltage is a device dependent property. Okay, we have also two models here. Often both models are used. Yeah, both are somehow exponential functions. One says e to the power of minus the field strength, and the other says e to the power of plus 1 divided by the field strength. So often both are used. So typical activation energies here in Black's equation are between 1 and 2.3 electron volts. So higher activation means stronger dependency on temperature. Low activation energy means lower dependency on temperature. To give you just a feeling, when you have 1 electron volt and you are at roughly 125 degrees centigrade, and you increase by 10 centigrade or Kelvin, then the failure rate will roughly double. And yes, with a lower failure rate, no, with a lower activation energy, maybe you need 20 Kelvin, yeah, for the same increase, for the same doubling. Yeah. No. Higher activation energy means higher failure rate. Yeah. No, we cannot say that. You were misleading. Higher activation energy means higher dependency on temperature. Of course, also important is always the basic failure rate. Yeah. So it's the basic multiplied with the temperature exponential multiplier. And in that way, but you could say one thing. Typically, of course, at high temperatures, higher failure rate, and also you could say if you have a higher activation energy and you go to a higher range, also that effect will be stronger. Okay. Then we have electrochemical models. Here, that model again has an activation energy, and here it has a humidity to the power of n, and H is the relative humidity you have here. I must say I'm not so happy with that model because in humidity you have more of a digital behavior. Yes. If it's below a certain value, you rather have no corrosion, yeah, so it's dry. You are beyond a certain level of humidity, it's wet, and then you can have corrosion. So in fact, that formula has been used, but yeah, as all of these models we have, we must see the limits, and so. Just corrosion is one of the most complex things. And in fact, modeling corrosion with mathematical functions often doesn't make much sense. Yes, temperature makes sense, vibration makes sense, temperature cycling makes sense. Corrosion, I would say, too complex. Wire bonds, again, you could say higher temperature, lower lifetime, just typically a diffusion problems. Then we have fatigue. For instance, we have a coil, it vibrates, typically Baskin curve. We have seen that. Probably if you come to the exam, could be we discuss about what is Baskin's curve, or for the Germans, Wöhler curve. Yeah. So I will not go into the details because we had a complete session on that. And also low cycle fatigue. Yes, here we have the delta T to the power of an exponent. Okay. Higher delta T means no lower cycles to failure. Now, I already mentioned where to get data, and people, especially users, tried to find out to find some representative data, and these trials just went back for many decades, and some have really collected data. And one of these was, for instance, Siemens company, which is a big electrotechnical company in Germany, now one of the biggest in the world besides General Electric. And Siemens had SN means Siemens norm, And here they had collected and they had data of fit for certain devices. The Siemens norm was also based, as far as I know, on reliability problems in equipment that Siemens had sold. Yes, so then they got information back. Then there were several aspects. Here I go to the back. Bellcore. Who was Alexander Graham Bell? Nobody knows? You heard about Bell Labs? Ah, yes, you are right. He invented the telephone. And then he founded a company, and that company was AT&T, American Telephone and Telegraph. And that company did all of the telecommunication in America until the 1980s. And then that company lost their license to be a sole supplier. Yeah, and the whole thing was broken up. For instance, the telephone company in California, for instance, they are called Pacific Bell. Yes, in honor of. What was invented in the Bell Labs? Yeah, yeah, of course. The transistor was invented there in 1945 or 46 or so. Okay. So the Bell Labs were in electrical engineering, you could say they were the most famous labs. Also Siemens had famous labs. AEG had famous labs, but I think Bellcore were the most important, and they also did work on reliability. And so they had a Bellcore database, and okay, you can see already the failure rates here are already quite different. For instance, for the IC, it is more than 10 times higher than for the Siemens database. All failure rates here are, let's say, computed back to the same conditions, 40° centigrade. Then there are several handbooks. The RDF was, I think, from the French communication. RAC was some free supplier of such data. And then there was a military handbook. The interesting thing of military handbook is that they tried to model all of the influences I have shown you in the formulas before in the reliability data. None of these databases is valid anymore. Yeah, there are too many devices. The life cycle of the devices is speeding up and speeding up, so they are not so long in the market anymore. Next generation, then data are outdated or can no longer be applied. So in that way, that was a nice trial, but in the end, it's not really valid anymore. Also, for many of these databases, you had to pay in order to get the information. Okay, and that was for devices. You could also say some of these also took into account, for instance, solder joints. Here, the military handbook, it said half a fit per solder joint. Siemens said 3 times 100th part of a fit per solder joint. So you can see all of these data are not really consistent. Okay, so that's a situation, and we must say that gives us a hint that it is not so easy to have really reliable and very precise data on reliability. So that was for devices. Again, we had it for individual components in mechanics. Now we had it in electronics. And now I would like to go more into qualification procedures. What is a qualification? So normally you make a specification for a system. Specification is something which describes what the properties are, and part of the specification is reliability. Yeah? So more on a general level, you could say it is the car must live for 15 years under some average conditions, and it must also be able to be used for 300,000 kilometers, for instance. Okay, that would be in a specification. It's a reliability spec. Of course, when you have a spec value, you must do two things. You must validate the spec. That means my specification, is it really valid? Yeah, for instance, are cars really used for 15 years? Are they used for a shorter period? Are they used for 30 years? Many, yeah. We have many cars now from the 1980s and 1990s, and so still driving around. And so in order to judge if a specification is valid, that is validation. On the other hand, the specification has a content. Yeah, the content says 300,000 kilometers. And to check whether the part you designed really survives 300,000 kilometers, that is verification. And verification is done how? By testing, of course. Okay, so that's important. Validation is a formal process, yeah. And verification is also a formal process, but also let's say an experimental process, a testing process, and that confirms what you demanded in the specification. Okay, now you could say when you look at systems, you typically have many sub-levels. Yeah, so you have a car, you have a subsystem like traction system. As a subsystem, you have the motor, engine. On the engine, you have the engine controller. The engine controller has devices, and okay, let's end it with that. You have the transistors in the motor controller. So that means you have several levels. Yeah. Typically, there is some company designing the car for which all of these parts are used. So he does this top-level specification, for instance, customer requirement 15 years, 300,000 kilometers. Now, on a lower level, you have a microsystem for, or let's say you have a sensor for as a gyroscope or such a thing. And the specification of the microsystem is derived from the specification of the car. So that's a top-down process. And to check whether the specification is correct and valid is again a validation. Now you have that microsystem as a device that, for instance, has several blocks like hardware, software, assembly and packaging, and all of these must be specified, yes, based on the specification of the complete microsystem. And now you go down again, so that is validated, and again, in the end, the designer takes a decision that material is used. Let's say that molding compound, or you have that package type. Is it a hermetic? Is it a plastic package? And so on. And also that specification must be validated. And based on these, in order to do that, of course, you always must have a guess how the system is designed. Yeah. So you do not have the complete design, but more or less a rough design enough, you can derive a specification on a lower level. And then the system is designed and built, and then it goes up. Materials are tested. What's the property of the molding compounds? Typically, that is not done by the car manufacturer, but it's provided by the supplier. Then the complete system is designed. Hardware, software are unified. Maybe you test it on a wafer prober. Then we package it. We test it. We test it on a test bench, and finally we integrate it. And in the end, it is built into a car, and it is tested there. Again, that is verification. That model is quite convincing, but it is also misleading. One thing is, it looks linear here, but it's rather like a tree going apart, because you have one system and you have many subsystems, and you have many more subsystems, and so on. And so it will go apart, and you would say you have many strings going like in a tree or in a branch, and then all of the things come together until finally we have a Mercedes car or so. Yeah. And in that way, that's a standard model of development and verification. Yeah. So specification, development, generation, and verification. Okay, that's important thing. And now let's go to a specification. That is also important. A specification must be correct. Yeah. You cannot give wrong values. You specify it must bear 100 megapascal, but you made a mistake. You should have specified 200 megapascal or such a thing. Yeah. So specification must be correct. It must be complete. So we have seen many failure causes. That means a specification must take into account all failure causes. Yeah. You cannot just say, I regard temperature, but I disregard vibration, humidity, current, density, and so on. So you must take all things into account that are relevant. That means complete. So it's a C4 concept. It must be contradiction-free. As I pointed out, when you, for instance, like in the aircraft wing, you want to have a certain braking force, and you specify aluminum as an alloy for building that. and you specify a certain weight. Yeah, it could be that that is not achievable. Yeah, due to the fact more material to make it stronger, higher weight or so. Yeah, so that means that also shows us that for such specification, we also must have an idea of the design. Yeah, so contradiction-free is important, and it must be capable to be verified and validated. Yeah, a specification where I cannot check neither whether it's valid nor whether the data I specify are achieved, that is worth nothing. So that's I just found it out. It's a C4 concept of specification. And in that way, specification is very, very important. Okay, let's go beyond the text. Another thing is that is I derived for MEMS, but also generally for mechatronic systems. We have three main parts. We have the MEMS hardware of the electronic hardware, you could say. Then an important part is software. Software is not so much important for reliability, it's more important for safety, you could say. And then we have generally all of the mechanical parts, yeah, around it, some hydraulic system or such a thing. And what is important, that all three parts are typically built in different factories. Yeah, we have the electronics factory, we have the software lab, and we have the mechanical workshop, for instance. And all three are different worlds, you can say. That's also important because it's a cultural problem. Yes, the people working in electronics, they studied electrical engineering, or they studied electronics and communications engineering, or such a thing. The people in doing software, still more and more, come from computer science. Yeah, not all, but many. Here you can say much of the software in embedded systems formerly was done by electronics engineers. But it's no more computer science. And then mechanical workshops, it's mechanical engineers or production engineers or so. Again, different worlds. These worlds, when you look at development, they have different tools. Yes. One has a layout system and such a thing, and simulating circuits using Mentor graphics or such a thing. The software people, they program in C typically, yeah, or a higher level language. And the mechanical engineers, they have a CAD system and maybe a certain finite element software also. So it's different tools they have different backgrounds. When you go into the three types of factories, they look quite different, yeah. And also talking to people is different. And these must be in a team, and all of the three, they do their job in their branch, you could say, yeah. And in the end, you must bring it together. All three parts must be provided in a correct and error-free mode. But in the end, it must function together. Yeah, you have a final functional test. All that also shows us when you are developing such systems, you probably will be a project leader, yeah. And that also means when you're here on top, now you consider it as a project, you cannot just say, okay, my background is software, and I'm not interested in mechanics, and I'm not interested in electronics hardware, or my background is electronics hardware. I'm not interested in software, and I'm not interested in mechanics. Yeah, that also means when you want to lead such a team, you must be able to understand and communicate with them, because otherwise you will not be successful. Okay, but that is really important. And now we must bring this together. And that's also an aspect which is really important, yes. We cannot just go with one view, but there are many aspects to be taken into account. And so electronics, software, mechanics, that's the worlds, and these must be brought together. Another thing is also important. That's the processes, and the process is the following. We have let's say a bigger factory like Bosch company. And now let's talk about sensors they produce, also gyroscopes, for instance. And then you could say, okay, at some time they started fabrication, and then they had one model, they improved it, next model, and so in production they have not only product one, but maybe simultaneously 10 versions, and at some time we have a new model. Similar thing in Mercedes car, yeah, C-Class or so, fifth type since 30 years or so, yeah, okay, or sixth type, okay. Because before it comes into production, we have a product development. Product development is really, let's say, based on the specification in the V model as we saw it. And so you could say when the product one was developed, then it came into production. What was also important is often, yes, we have a factory, and that factory has a certain technology. Yeah, for instance, surface micromachining or bulk micromachining or VGA soldering or such a thing. And typically the basis for a product development is a fabrication process. And both the product development and the fabrication process development, they are often independent. Yeah. So the production manager, they say, okay, what is our technologies we need for the future, for the next 20 years? And we select it in a way that our developers, our development departments can design modern products which can be later on produced, yeah, in a later phase. And then there is something important even before that. We must have a certain research. Research is a first step, for instance, to find out are certain fabrication processes suited. For instance, here in the research, maybe around the year 1980 or so, the Bosch company, they developed surface micromachining. Yeah, and later on it was converted to a factory who did that, MEMS factory. And based on that capability of that factory, products were developed. And later on came into fabrication. So I was always astonished. I came from industry, but often we had, even for a long time, we had students doing a new microsystem, yeah, just a special type. But but often it was not, it was a good idea or for some medical application also, but what was, what not really understand also by their supervisors is that when you do that on a university level, you are here, yes? What, for instance, Professor Stieglitz, who is doing biomedical engineering, is he had to do decades, really decades of fabrication process development. And later on, they had a spin-off who did product development, and they could then use fabrication processes. But in the beginning, there were many developments or research, and my father also was in research in industry. He told me, yes, 10% of what we really researched was later on used, 10%. And that's a typical value. And now when we have that product life cycle, I want to come, that was important to show you how development processes go. On the other hand, in the product life cycle, here one aspect is reliability. And depending on which phase we are here, we have different targets of testing. When we have, I think I already mentioned that story of my bosses talking about, we test for 200 cycles. No, we test for 1,000 cycles. We test for 3,000 cycles, so we are better. And we test until infinity, yeah? Okay, I think I told that story, and what was the difference? One was from research, one was from fabrication process development, one was from product development, and one had a production line running, yeah? So what is a target in production? In production, you want to know two things. One is every single property of your product is within tolerances. That is any property you have, and you test any property. And the second is also the reliability must be better than something, yes? And so you test a limited number of parts for a limited time, because you produce parts and you want to sell them, and you don't want to wait for months until you know the reliability, and also often you do not have the statistics. So and then you specify, okay, short time, not so many parts, but no failures allowed. Now, if you have failures here, and if it's only one, it's a problem for your complete production, yeah? But you want to avoid that. In the product development, you do more, yes. You go really with a complete product into more or less realistic testing conditions, and you verify that your specification is maintained, yeah? Okay, so here you test for a longer time, under more realistic conditions, and with a limited acceleration, of course. Okay. In the fabrication process development, often reliability is not so important, yeah? And in the research technology development, you want to know what the end of life is. That means you want to see where the bathtub curve goes up, yeah? And of course, here you investigate what are influencing parameters I already mentioned, delta T, time of cycle, and. All of these influences are investigated, and the impact of the influences on the number of cycles to failure, for instance. When you go into fabrication process development and you have a certain factory, you sometimes have more parameters which are relevant. Yeah. So here you do that on prototype basis or on dummy basis or so. And here you also have influences which are specific for your fabrication line. For instance, you have a electroplated layer and you generally had some influences, and now the plating bath has an influence again on some reliability or strength of a metallization, for instance. And here that are fabrication process specific influences. But in the end, in the research and technology investigation, you want to know the end of life curve. Yeah. On the other hand, when you have a running production, you just want to be sure you do not make mistakes. Yeah. Okay, and that's a reason why it's really important at which phase of the development or of the product generation cycle we do the testing. Okay, that is specified here. I also already mentioned it. I put it together in a table. Maybe you have a look at that here. Now maybe just some rules in order to develop dependable products. Okay. One we already mentioned, we must have a valid specification. Okay, the C4 is already mentioned. Then another rule is minimize the number of parts if possible. Sometimes in a part you have more elements, for instance, in microelectronics, but by putting more transistors on, cramming more on one chip, you also can increase reliability, because you can say you always treat that as a chip, no matter how many transistors it has. So no risky components. That is, sometimes you have components which are not so robust, where you sometimes can have more failures or early failures or so. Then when there is degradation and wear, you want to have replaceable parts, yes. Of course, when you have a printed wiring board assembly, that assembly you cannot repair normally in most cases. Do not use the safety margins completely. Yeah, so keep away from the limit. Early testing is important, because one thing is the idea you have what can fail, and the second is what really fails. Computer simulation is important, especially in the development phase. Okay, that like finite element simulation, but also in dynamic systems, it's very important, or in systems where certain processes develop, simulation is important. Important is also vibrational behavior, because vibrational behavior is very complex. And okay, also here testing and simulation is important. Then experimental verification, of course, and both. So the testing of the product, both under test bench conditions. So here you have a good control of the influencing parameters, and under realistic conditions in operation, because here you have more interactions, which could be relevant. Then it is important to have stringent quality controls in-house and for the suppliers. In fact, when cars were built, initially there was a job of driving the car around the quarter in order to check whether it is okay or not. Yes. In most companies, this has been abandoned, but you have so many individual checks before the car is released, then they think it is not necessary. Provide intermediate checks in production. That is what I said. Just relying on the outcome with respect to reliability, you cannot really control it because the statistics is too bad. Yes, short time testing, only limited number of parts, and therefore all of the intermediate checks are important, that everything is in control. The basic idea behind that is, if a part is stronger or if the strength is controlled better, it will be better for reliability because the overlap of the two curves is less. Yeah. And that means if you have that intermediate control for any property in production, it will be good also for reliability. And what is also important, and my data I got was, for instance, evaluation of warranty statistics. Yeah. And that gives you information how good your product has been, at least in the past. Yeah. Okay. That was it for testing. And so it is very important to know that testing is related to reliability, but it is also related to the phase in which we are with respect to product generation. Okay, thanks for your attention.